We are looking now at the tutorial solutions for external flow and drag, that is drag and lift. In question 15-9C, we are asked to define the frontal of a body and discuss its application. Okay, as you can see, the frontal area of a body is the area seen by a person when looking upstream. That is the area projected on a plane normal to the direction of flow of the body. The frontal area is appropriate for use in drag and lift coefficients for blunt, or sometimes they are called bluff bodies, such as cars, cylinders, and spheres. You can look at the example 15-21 just below to give you an idea what is meant by the frontal area. If you look at the sketch annotation that I have just done, you can see that if you project the plane AA towards the eye, or what the person looking at the section of the car as you section it across, AA will look like, that is called the frontal area. Okay, we've just erased that annotation because now we need to look at question 15-21. Here you are asked to measure the drag force. In fact, the drag force is measured in a wind tunnel. The drag coefficient of the car at test conditions is to be determined. Now, before any proceeding any further, you need to review the assumptions. First assumption, the flow of air is steady and incompressible. Secondly, the cross-section of the tunnel is large enough to simulate free flow over the car. In other words, you do not want the tunnel periphery to interfere with the flow, causing false reading on the drag of the car. Thirdly, the bottom of the tunnel is also moving of the speed of the air under actual conditions. So presumably, you must have some sort of belt, conveyor belt, which is moving, or if you do not have that, you will probably have to assume that there are some errors going to be introduced, and this effect is negligible. Next, the air is an ideal gas. You will learn in thermodynamics, if it is an ideal gas, it will obey a certain law or rule called the perfect gas equation. Okay, for this particular condition, we are told at 25 degrees, and looking up tables, we can find the density of air is 1.164 kilograms per cubic meter. Okay, the drag force acting on the car body and the drag coefficients are given by the following formulas. The drag force is equal to the coefficient of drag multiplied by the frontal area times rho v squared over 2. So making the drag coefficient the subject of the formula and remembering what is meant by the frontal area. In this case, we are given the frontal area, okay, as the width and the height of the car, and we know the velocity is 90 kilometers per hour. We have to divide by 3.6 to get meters per second. We know the density and we get the drag coefficient as 0.33. It is worthwhile to note the discussion that the drag coefficient depends on design conditions and its value will be different under different conditions. Therefore, published drag coefficients of the different vehicles can be compared meaningfully only if they are determined under identical conditions. Okay, so we will now look at question 15-64. Okay, as you can see, I have started this question. It's very important that you know how to define and discuss stall. The decrease of lift with an increase in the angle of attack is called stall. When the flow separates over nearly the entire upper half of the aerofoil or the airfoil, the lift is reduced dramatically. The separation point near the leading edge. Stall is caused by flow separation and formation of a wide wake region over the top surface of the airfoil. Commercial aircraft are not allowed to fly at velocities near the stall velocity for safety reasons. You'll be surprised that this angle is usually around 15 to 18 degrees angle of attack. Airfoils stall at high angles of attack. Flow cannot negotiate the curve round the leading edge. If a plane stalls, it loses much of its lift and can crash. Note, angles of attack above the stall angle, the drag will also increase significantly. Question 15-76 is a pretty standard question, but it's worth looking at it in detail. In particular, the wing area, let's go through it. The wing area, the lift coefficient, and the takeoff settings, the cruising drag coefficient, and the total mass of a small aircraft are given in the question. You have to determine the takeoff speed, the wing loading, and the power required to maintain constant cruising speed. Here, you start with your assumptions. The first assumption, the standard atmospheric conditions exist. Since we are not told about the height of the aircraft, the drag and the lift produced by parts of the plane other than the wings are not considered. The density of the air we are going to take as 1.225 based on the conditions given. Now, it's important to realize an aircraft will take off when the lift equals the weight. Therefore, the weight of the aircraft is equal to the force of lift at the moment of takeoff. So we equate the weight with the lift force. The velocity now is in fact the velocity at which the aircraft will generate sufficient lift. We make V the subject of the formula, the velocity. On the right hand, all are the terms that are given. Okay, in this case, we are given everything on the right hand side, where the weight translates to 2 mg. We are given the density, the coefficient of lift, and the area. We then get 56.4 meters per second. This translates to 203 kilometers an hour. It's good to remember that 1 meter per second is equal to 3.6 kilometers an hour. So let's write that down. Next, the wing loading is the average lift per unit planform area, which is an equivalent to the ratio of the lift to the planform area of the wings, since the lift generated during steady cruising speed is equal to the weight of the aircraft. Therefore, the loading is given by the weight, assuming the aircraft is not rising or falling, which is W. You know that the aircraft weighs 2,500 kilograms or 2.5 tons, and the planform area of the wing is given as 28 meters per second. So the wing loading is 876 Newton per meter square. Finally, when the aircraft is cruising steadily at constant altitude, the net force of the aircraft acting on the aircraft, the vertical force, is zero, and thus, the net horizontal force acting on the aircraft is zero, and thus the thrust provided by the engines must equal to the drag force. So the drag force is given by the earlier formula which was written down, and you know the drag coefficient which is given, and all the other data, the area, the density, the velocity in meters per second gives you 4.168 kilonewton. So this drag force is balanced by the thrust. And note, I think we have dealt with this quite many times, the power is force times velocity. The propulsive power required to overcome this drag is the thrust times the cruising velocity. So you know the thrust, which is 4.168 kilonewton, and you know the velocity is 300 kilometers per hour, but you have to change it to meters per second, and you get 347 kilowatts. So the engine must supply 347 kilowatts of propulsive power to overcome the drag during cruising. Finally, it's worth looking at the discussion. The power determined above is the power to overcome the drag that acts on the wings only and does not include the drag that acts on the remaining parts of the aircraft, the fuselage, the tail. Therefore, the total power required during cruising will be much greater than this 347 kilowatts. The required rate of energy input can be determined by dividing the propulsive power by the propulsive efficiency.